Good afternoon, good evening, depending on where you are. Thanks for the invitation from Professor Tianxiao. It's my great honor to attend this workshop. I come from the Beijing Institute, School of Integrated Circuit Science and Engineering, Beihang University. For the Beijing Institute, the founder of this institute was actually supported by Albert Furch. Maybe some of you never heard of Beihang University. Beihang University actually located is in Beijing of China. Its location is close to Peking University and Tianxiao University. And this is our beautiful campus. And also this is our school lab building. My topic today is talk about the room temperature ferromagnetism in the 2D van der Waals arrangement toroid and give some potential application. Before that, I will give the outline. First, I will give an introduction to this 2D material, and two is experimental result, our recent work. First is tailoring ferromagnetism in arrangement toroid through the heterostructure of bitumen toroid. Second is the work about SOT switching in this heterostructure material. This work, we are still working on that, not published yet. And the third one is terahertz emission in this heterostructure. Also, we are working on that. And finally, I will give a small summary. As well known is the 2D material since the discovery of the graphene, just like Professor Stevens already talked about a lot about graphene, and the 2D van der Waals material has become the very hot topic since after so long time. This 2D van der Waals, the material from already become a family. It covers the material from the metallic material like graphene to semiconducting material like black phosphor, and to the insulating the 2D material like boron nitride. And in all this material, there are several very famous and very popular types like 2D carbonide, 2D oxide, and perovskite type. And why is 2D material is so interesting? And the first thing I think is the 2D material. The van der Waals material is 2D state, and it will has a lot of quantum phenomena. And second, it's easy to build the heterostructure. And this kind of heterostructure in 3D material is very difficult. And it will integrate different functionality in one unit devices. This is just showing in this picture. You can see, you can model the sulfide, boron nitride, and tungsten selenide. You can easily to get this kind of structure and build this kind of, I think it is proposed mode. And you can easily get the pin junction in different materials, the 2D diode. And also you can see, you can get the vertical transport, the pin junction, and also the double gate, the structure. I think this kind of structure is very hard to be built by the 3D material. Actually, today my topic is about one specific 2D material is ferromagnetic 2D van der Waals material. It will introduce the spin in the 2D van der Waals material. As well known, spintronics has already passed for 30 years. This is just so many interesting phenomena, just like GMI was discovered by Edford and Peter Grover, and also TMI effect. Both the effect has already been used in the hard drive, and the density, the storage density has increased a lot. Right now, already changed our world. In the 2D ferromagnetic material, actually, in the theoretically and experimentally, it has found more than 10 types of this kind of material. But in all these materials, the most stable one and also the intrinsic material. Right now, it's mainly focused on the 3 type material. One is chromium germanium telluride, one is chromium iodide, and one is iron germanium all these material are intrinsic material, and iron germanium telluride it has almost the highest Q temperature, 220 Kelvin, close to room temperature. And this material recently have attracted a lot of attention. All this material is normally it is fabricated by the mechanical exfoliation method, like graphene, to get to 1 monolayer of this material. It's very easy to get this material by this way. But this method is actually, we know it's difficult to prepare in large quantity. And also it's hard to make a device, and also hard to control the thickness. So we know always searching for the large scale method is always a hot topic in this 2D material. And another thing, if we want to use this 2D ferromagnetic material, we need the room temperature. So that there have been a lot of work to control the magnetization by different ways, like gate control, string control, and interfacial control. This PPT shows, this page shows some already reported material, like chromium germanium telluride. You can use ionic liquid by gate to increase its Q temperature. For this chromium iodide, you can use the gate to change this material, the magnetic phase from the antiferro to ferro. As in iron germanium tellurides, it's very interesting. You can get room temperature ferromagnetism by gate tuning. And also you can, in this material, you can use the patting method, etching. Also you can get room temperature ferromagnetism. But in this way, the ferromagnetism from the PMA to the implant and short wave. All this interesting result has inspired this field. However, all this method is still hard to get room temperature in large scale, and also maintain the very stable magnetism. So this is also another concern, how to get the room temperature ferromagnetism in large scale. The good luck thing is several years ago, the iron germanium telluride, this material can be grown by MBE. This method gave a way to get the large scale growth. So in our work, we also focus this iron germanium telluride material just because it has almost the highest intrinsic Q temperature. But we introduced the topologically insulated bismuth telluride with this material. Why use the bismuth telluride? We know the bismuth telluride is very extracting material, especially when the bismuth telluride, when combined with some other non-magnetic material, it can change the non-magnetic material to ferromagnetic material by proximity effect. So this is the reason we think it's possibly by this way the iron telluride could be, the Q temperature could be enhanced. Based on this, we first give a theoretical calculation. Iron telluride is kind of itinerate ferromagnetism and follow the AC mode. By calculation, we can see from our experiment, from the simulation, we can see the exchange coupling between irons in the intralayer has significantly enhanced when compared to the pure iron germanium telluride. Follow this theoretical calculation, we do our work by MBE. We grow the iron germanium telluride on bitumen telluride. Our MBE system could maintain the vacuum of 10 to the minus 10 torr, and all the material resource was evaporated by loading cell. This is the structure, elastic structure of the material, bitumen telluride at the bottom and iron germanium telluride on top. And from the read pattern, we can see a very clear 2D streak pattern. It means the surface is very smooth, and it also is crystal structure. And the bitumen telluride, it shows this terrace structure is a typical topological insular surface. And after growth, the iron germanium telluride becomes smoother. And from X study, we can show that we can get the very good crystal bitumen telluride and iron germanium telluride. And the TM result, we can see the van der Waals gap in the iron germanium telluride. We give the magnetic transport measurement to see the pure iron germanium telluride. It shows the metallic behavior for this material. And the Q temperature is 150 nanometer iron germanium telluride. Its Q temperature around 220 Kelvin. And also it showed the very below the Q temperature, very clear the history loops. And also, and very interesting close this, the coercivity, there is a shrinking behavior. That's because a domain structure formed. Actually, when we make the film thinner, go to 30 nanometer, this domain structure disappear, only show this kind of the very square loop. Also, from this loop, you can know that this material is a PME feature. Very interesting thing, when we grow the iron germanium telluride on the bitumen telluride, this is 5 nanometer iron germanium telluride. It still keep the metallic behavior, but the Q temperature we can see over the 220 Kelvin. This is the pure iron germanium telluride. The Q temperature, this is the heat structure. The Q temperature is already very high. Even around 380 Kelvin, you still can see a very small hint of this anomalous Hall signal. And also, this is the implant. We work on the implant, the anomalous Hall. We can see very clear this history loops. That means the very clearly prove this is a PME material. And also room temperature, we can see this loop. Also, we do the mock measurement. We can see the prove again this room temperature, ferromagnetism. And also, we measure the squid, and from the 300 Kelvin, you can see very clear the hysteresis loop. Also, we give calculation for the interfacial PMA. We can see the PMA is around 0.6. Compared to our recent work on the cobalt boron, it's close to the worst case in the cobalt boron. We know the PMA is very important for the MTG. The high PMA can make the MTG more stable, some more stable. So I think in the future, probably after optimization, the growth, the iron germanium telluride, this material has a possibility to work on the MTG structure. And also we work on the thickness-dependent magnetic property in this head structure. We continue work on other thickness, 3 nanometer, 4 nanometer, and 10 nanometer. We can see very clear at low temperature, all the structure can see very clear hysteresis loop. And about room temperature, very interesting also for the head structure for 3 nanometer, around 380 Kelvin is we still a little bit see the hint of normal hole. And for 4 nanometer, around 40 Kelvin, we still almost see a small hint normal holes. Means the head structure definitely already above the room temperature. About the 10 nanometer, this Q temperature a little bit lower, around this room temperature, the TC around the room temperature, a little bit lower than the 3 nanometer and 4 nanometer. All of this head structure definitely can prove because of the bismuth telluride, the iron germanium telluride, the Q temperature has been enhanced. We make a small comparison between iron germanium telluride and the head structure. For the iron germanium telluride, the Q temperature is always around 220 Kelvin. But for the head structure, it's over 300 Kelvin. The TC little bit depend on the thickness. And we summarize the TC and the layer thickness. We can see for the pure iron germanium telluride, when the sample is thinner, the TC become lower. However, for the head structure, when the sample becomes thinner, the TC increase. From this, we can know this TC enhancement is from the interfacial reason mechanism. So this can also prove our theoretical calculation. This is the interfacial enhancement effect. It's already published. It's a nano. Because this material is very new, so we want to use this material for the device. So we also check the thermal stability in the atomic sphere. This is the TM after the one month growth, sample growth, and we can see almost 2 nanometers iron germanium telluride. And we also do the XPS measurement to carefully check this material, the evolution in the atmosphere. We can see in this material that germanium and iron is actually very easy to be oxidized. The tellurium is a little bit hard. Even after a long time, this is still this is 40% left. And after a very long time, this material for germanium and tellurium will become this kind of oxide. And for the iron, it's very interesting. It will change from the different type of oxide. Finally, after a very long time, it will become iron. It's carbon oxide. It's very interesting changing in the air. The second, I will little bit talk the SOT switching. Maybe the time also so many left. I will quickly. We know this 2D already have some proposed device like 2D TMR, the spin logic, and also one is very important, the 2D SOT device. Because we know the SOT is actually very important and the next generation of the method for MRAM. So to investigate this the material, the 2D material of its SOT the property is very important. Actually, there are already 2 papers published last year and 2 years ago. One is from the Professor Guo Qiangyu from the Chinese Academy of Science of China. One is from the Professor Shi Jing from the UC Riverside. They use the platinum combined with antimony telluride. They can realize the SOT switching. However, how to realize the room temperature, the SOT switching, and how to get the O2D SOT devices, don't use this kind of the 3D material. That's still a very good, very good concern in the future. Actually, one good material is to integrate it with top-load insulator. Top-load insulator we know has a very high spin Hall angle compared to the already used the platinum tungsten. This already lot of people that reported this materials the spin Hall angle, especially with the cobalt and boron. This 3D material, even at room temperature, use this material, you still can get a very high spin Hall angle. And this work we didn't finish yet. But we use this top-load insulator with antimony telluride. We can realize the room temperature SOT switching, and we can see is the magnetic field dependent SOT switching. That is because this material, top-load insulator, is very complex. It has a topology surface state as a box state. And also in this 2D van der Waals material, heat structure probably has the 2D EG gas interface. So we are working on how to distinguish all the three effect. The third part, I will talk about the terracotta emission in this top-load insulator and the antimony telluride structure. We know is the terracotta is very it's a kind of radiation from in the range of 30 microwave meter to 3 millimeters in the frequency range of 0.2 terahertz to 10 terahertz. It's very useful. Can use be in the radar, for the safety check and medical check, and especially in the 6G communication. Traditional terracotta source, you have so many like DSTMS, lithium niobate crystal, and zinc telluride, and photoconducting antenna. All these traditional terracotta sources have itself the advantage that it's the disadvantage. Disadvantage including the maybe expensive and also maybe very big and short lifetime. And since 2016, Professor Kim Yeo reported that spintronics also can be used to emit the terracotta. So a lot of work already work on this. This mechanism should have the strong inverse spin Hall effect. Recently, we work on this field. In the traditional material, cobalt and boron, we can realize the very big size spintronic source, and its emission intensity comparable to the zinc telluride, the commercial zinc telluride. And to work on the top-load insulator iron germanium telluride, we also check the top-load insulator itself, the emission. That's two mechanism. One is the linear photogalvanic effect. One is the circular part photogalvanic effect in this POTI structure. After remove this kind of structure, this mechanism we can get the terracotta emission from the heat structure. we can see that because topological insulator has a very high spin-Hall angle, so in topological insulator with iron, this kind of structure, its emission intensity is almost comparable to the combined bond three-layer structure. That means can prove it have high potential for this terahertz emission. And follow this, we work on the topological insulator and iron germanium telluride. Actually, it can give emission of terahertz. However, the intensity is not so strong yet. But this is the first demonstration of terahertz emission in the 2D ferromagnetic material. This work, we're still working on that. Give a summary. First, get Q temperature material about room temperature in 2D van der Waals for the ferromagnetic material. Second is SUT switching is in 2D ferromagnetic material. And third one, room temperature terahertz emission also in 2D ferromagnetic material. Thanks to my collaborator and the Professor Wei Shengzhao in our school, and Professor Wu Xiaojun in Beihang University, and Professor Kang Wang in UCLA. Thanks for your attention.